Okay, welcome. I believe we are now streaming. Hi, everyone. I believe we're streaming. I'm just double checking if this is working. Thank you for joining us. Um, just checking again. Yeah, we are live. So it's going to appear on my end any second now. Perfect. Yeah, this is Flower Monthly September, folks. Thank you for joining us. My name is Nicholas Lane, and we're about to get underway. We're also going to start our webinar for those who are in the webinar room. And, and we are now all operational. Great. Well, welcome to Flower Monthly September. We have an amazing show planned for you today. Let's get straight to it. So my name is Nicholas Lane. I'm going to walk you through the agenda and sort of run today's proceedings. What we're going to do is start as per normal with a flower update. We're going to examine what's the latest and greatest in the flower community and the things to watch out for in the preceding coming 13 days of September. And then we'll shift gears and go to the sort of main event of this community session and see two presentations from our speakers. We're going to start with a presentation by Meghali Nandi. She is at the University of New South Wales, Sydney, and she's going to be talking to us about uses of federated learning in the context of noisy layers and ways to approach solutions to those problems, in particular when we care about building explainable AI. Next, after her presentation, we'll switch gears to another one. This talk is going to be about Argos. Argos is a federated system for detecting traffic signs in the real world environment using federated methods. It's going to be presented by Mahdi Jahadi. He's currently at the University of Michigan. So yeah, welcome both of you. Thanks for joining us today. Really appreciate it. Let's take a look now at our flower updates for the month of September. Well, our first major update is Flower AI Day. Flower AI Day is going to happen September 25th in San Francisco. It's an amazing event. We're holding it at the Ferry Building in downtown San Francisco. The focus is going to be about how open source, decentralized superintelligence is here. It's here in many different forms. It's being used all across industry. It's being used in research. And it's only ever going to get better and better and better from this point forward. The day will be a celebration of how far we've gotten in this direction. We've already got some incredible speakers released, people like Sarah Hooker, people like Tony from Red Hat, and a number of other speakers. We've still got a few other tricks up our sleeves. So you'll be hearing more speakers being released as we get closer to the event. We'll be kicking off at about 1 p.m. on the 25th, and everyone's invited. I hope to see many of the flower community there, as well as people who are new to the space who just want to see what is really happening in terms of AI's next big step. So that's obviously a huge thing for flower happening this month. It's been so successful. We've had so much sort of like people asking about how they can participate more actively. And so we've decided it's time to run a big hackathon. So we're going to run this hackathon at Stanford. It'll be on the day after AI Day. So AI Day is on September 25th, on the Thursday. On September 26th, we're going to head on down to Stanford. We're already actually close to capacity for this event. In fact, actually AI Day just closed its early bird tickets just now. I saw we've sold the last of those. So both are pretty close to capacity. We're really delighted that Stanford has allowed us to run on campus. We're going to have primarily this big 8-hour hackathon that starts in the morning. But there's also going to be talks and demos and a big community extravaganza. I know about a third of people registered so far are registering just to see what's going on and see the demos, see the hackathon going on. We've got people participating actively in building things in the direction of decentralized methods from a number of companies. For example, Apple, Salesforce, Meta, in a number of schools. So obviously Stanford, we're right on campus, but also CMU Silicon Valley campus has a big presence. Berkeley's bringing a big team. So it's going to be fun. Can't wait to see what's going on there. Awesome. Please register for both these events if you're interested. Two more things I wanted to highlight before we get to our great talks. And that is Flowers hiring. We are looking for fantastic people able to communicate our mission, which is to take decentralized and federated methods mainstream. We're interested in people who are really sort of able to navigate social media, help us communicate this important mission. So if this sounds like you, take a look at the full description here on the Flower site and submit an application. And the last thing I want to highlight was Flower Enterprise. We had our huge launch event at the end of basically July 31st. The recording of these different sessions we had on that day are now available. Session 1, I think, is actually my personal favorite. I've placed the URL there if you'd want to take a look. But if you're interested in Flower Enterprises in general, there's the URL at the bottom. You can book a demo. Something that is going to be going live very soon this week is a one-pager. We've had a lot of people asking us, is there a flyer that describes the Flower Enterprise offering, how it can enable companies, large-scale organizations to quickly take their concept of a federation they want to build to deployment and production in minutes. And so we've got this sort of one-pager snapshot on what Flower Enterprise can do and how it can enable those sort of outcomes ready for folks to use. If you want to get a copy of this one page, it'll be on our website shortly, or contact us and we'll love to discuss more with you about Flower Enterprise. So that is the sort of snapshot of Flower for the month of September. I'd love now to transfer to our first technical talk of today. As you heard earlier when I was talking about the agenda, we're joined here by Meghali. She is at the University of New South Wales in Australia and been doing fantastic work in building federated systems. And so I can't wait to see what she's found, what she's learned, what she can share with us. So over to you, Meghali. I'm super interested to see your work.
Yep. I'll share my screen.
Yeah, yes, please.
I hope it's visible.
Yes, looks great.
Okay. Hello, everyone. I'm Meghali Nandi, and I'm really thankful to Nick Lane for inviting me for this talk. I'm here to present our work, Nosy Layers Noisy Fixes, Tackling DRAs in Federated Learning Systems using Explainable AI. This work was accepted at the 28th ACM Asia CCS conference, which was held last month. I'm currently a PhD student at UNSW Sydney in the CTI lab, and I'm under the supervision of Dr. Arash Shagagi and Dr. Sanjay Jha. And I've also collaborated with Dr. Nazatul Sultan, Gustavo Batista, and Raymond Zhao from CSIRO. So what I'll be covering is, first of all, I'll be just giving an overview of federated learning and the current data reconstruction attacks. That's the DRAs. And then this paper was on defenses against DRAs. So I would be describing about why the current defenses fail and the problem statements that we have tried to solve. Then we come to our solution, that's the Dr. Armor, and the results of Dr. Armor. Starting with what is federated learning happens across 3 rounds. First is the model initialized. A model is initialized by the server and it's sent to the clients. The clients updates the model and trains on the local data and sends the updates to the server. The global model in the server is updated using the weights sent by these clients. Now, whenever there is a system that's launched over the internet, the next news we hear is there are some attacks happening, right? So even for federated learning, we have three kinds of attack scopes. First is the client side, the second is the server side, and the third is during the communication between the client and the server. Here we are working on a server side attack, but the defense is from the client side. So one of the server-side attacks is the data reconstruction attacks, where the server is the entity, malicious entity. So the server, when it's sending the model to the clients, they basically do some modifications on the model, which can be used to give out the weights from the clients, and those weights can be used by the server to reconstruct the data. So that is the data reconstruction attack. And why we have this nosy layers is influenced by the one of the recent attacks, that's the low-key attack, where the malicious architectural components are added to the layers of the models and sent to the clients. Now, the effect of the DRA is it can reconstruct the data and also identify the client from which the data has been coming in. The DRA works because the gradients from these malicious layers can be used to reconstruct the data, and the current existing defenses do not work because the attack remains effective even when the aggregation is in place. Now, coming to the image on the left-hand side, this is the low-key attack. So they have the convolutional layer, which basically helps in the identification of the clients. And then we have the convolutional output, the FC1 and FC2, the three layers which has been added by the malicious server, and the data used, the data coming out of these outputs can be used for the reconstruction of the images at the server side. So why existing defenses fail against this attack? We have multiple defenses like the secure aggregation, Byzantine resilient aggregation, anomaly detection, differential privacy, gradient compression and pruning, and limiting mutual information. All these types of defenses basically tries to make the updates or the weights sent by the clients in a secure way. Like using monitoring or basically identifying what kind of outliers are there. But however, all these kinds of defenses were surpassed by the low-key attack. Now, differential privacy is one of the defenses which will work for any kind of attack. However, this will lead to accuracy degradation because there is a costly trade-off between the privacy and the utility. So why addressing these attacks is crucial? Federated learning was launched because we needed the security and privacy of the data, which is existing in the client nodes, right? And we also need to have the performance of the global model to remain effective, and the accuracy and effectiveness of the global model should be maintained. So because of those reasons, we need to address these attacks. Now, with that, we come to the two problem statements that we have tried to solve in this work. First is we need to identify the malicious layers that's involved in the DRAs. And second is after identification, we need to defend against these DRA. So here we have basically tried, the motivation is when federated learning was launched by the Google. So they said that whatever model is sent to the clients would be acting as a black box. So whatever the server sends to the clients, they would be training it on their own data and sending the weights. Now here we have taken a completely different approach. We have tried opening the black box. We are trying to give the control to the client, treat the model as a white box, and we are trying to understand the layers of the models and how they are contributing to the output of the original model architecture. So coming back to the low-key attack, here we have these, suppose this is the model architecture, the original model architecture, and the first three layers have been added according to the low-key paper. And these are acting as the malicious layers. And this is the original model architecture with the output layers, which will act as the non-malicious layers. Now, suppose this model is having this image as the input and it outputs cat as the output. Now, these three malicious layers are because these are malicious and they are leaking gradients which are used for reconstruction of the data. These three layers are not supposed to be contributing to the output of CAT. Rather, the layers which are used in the original model architecture should be contributing to this output, right? So that is why how we can solve whether a layer was able to contribute to the output or not is using the XAI, that's the explainable AI. So we come to the first solution, that's the explainable AI. It basically refers to the methods and techniques that make the results of machine learning models understandable to humans. It gives us trust and transparency. It mitigates any kind of bias in the AI models, and it's also user accepted because it gives clear explanations for AI decisions. Now, the methods used by this work, because it's the first work using explainable AI on DRS, we have used layer-wise relevance propagation, that's the LRP, and deep Taylor decomposition, that's the DTD. We have used LRP for smaller datasets and smaller models, and we have used DTD for larger models. The reasons for this is properly explained in our paper. Because we have a constraint in time, I'm not going to go into the details of this. Now, this is a layer-wise relevance propagation where we have the cat as the output and we go from backward to forward. So basically, we're going from the output to the input and trying to understand how each of these layers are actually contributing to the output. So now, whenever the malicious layers, which are sending gradients, they are not contributing to output, we can flag them and identify that these layers can be malicious. And that is how we were able to get the results. Now, coming to the PS2 solution, where this is the mitigation strategy, where we have identified the malicious layers. Now we need to give the control to the client on how to defend it, right, against the DRA. So we have proposed two solutions. First is the noisy fix, where we have added DP, and second is the pruning layers. Now, one may argue that differential privacy is already existing. What's new in this? Now, here I would give the argument that we have added one extra step here. Differential privacy in normal federated learning systems is added to all of the layers outputs, right? Now here what we have done is we have identified which layers are malicious and added DP to only those malicious layers. In that way, we do not care if the privacy utility trade-off of those layers are affected or not. So in that way, we have used the noisy fix, that's the differential privacy. And the second is the pruning layers, where we have added skip connections to the non-malicious layers. That is, we are completely skipping the malicious layers training and just adding skip connections to the non-malicious layers. So these two are the solutions for the mitigation strategies. Coming to the results, first is how we have detected of the malicious layers when the layers are at the start of the model. So these red marks are basically the malicious layers, and we were able to use the explainable AI to show that these are the malicious layers, whereas the rest of them were not. This is a detection of the malicious layers when it's towards the middle or towards the end of the model. This was randomly generated, and again we see that with using by the red flags, we are able to detect the malicious layers. Now, the mitigation strategy was the adding the noise. So we have used pixelation here. One of the results was pixelation, where this is the original images, and this is the DRA using the Loki paper, and this is the pixelated images. We are not able to understand what the images are. The detection reliability is where we have found that the TPR and TNR of across the 5 datasets that we have tested on are pretty good. However, when we come to the detection reliability, when 3 malicious layers are inserted deep in the model using these explainable AI systems, we see that for ImageNet, we have a little lower TNR and TPR values. This is because we have used LRP in the larger images, in the largest datasets, which is the ImageNet, and the model structure was also pretty large, because of which the TPR and TNR were reduced. However, we have also proposed that when we use much more complex explainable AI systems, these results are actually able to improve. Now, the impact of Dr. Armour on the FL accuracy, we wanted to check how our defense is actually affecting the FL accuracy. So this is the Dr. Armor without with the noise and the Dr. Armor with pruning. We see that there is a slight decrease in the accuracy, but we have argued that with this, we are able to get the required utility of the system rather than leaking the data from the client devices. This is the poisoning impact on the accuracy of Dr. Armor, where we have tried using continuous and periodic poisoning, and we see that even with continuous and periodic poisoning, we are able to use the Dr. Armor, and the accuracy of the models were completely increasing and not getting affected by the poisoning. And here we come to the comparison with other defenses, where we have compared our work with the normal pruning, DP Laplace, Guardian, DP Gaussian, and Soteria. And we see that this is our Dr. Armor, and we are able to leak pretty less number of images, and the leakage rate is pretty lower to the rest of the defenses that were already existing. And the main reason is because we have tried to identify the layers. The rest of the defenses were trying to get a privacy utility trade-off on their systems. But here we do not care about that. We have already identified the malicious layers, and then we have done the defense. So that's the reason. So coming to the conclusion, the motivation behind this work is that current state-of-the-art DRAs make model modifications. So basically, these make the models detectable on the client side. And how we are detecting is we have given the control to the client to treat the model as a white box and use explainable AI. And after identification, the mitigation strategy was to add differential privacy or prune those layers only to the identified layers. Now, once that we have done the defense, the next frontier that we are working in our lab is to design a stealthy and undetectable threat, which can evade detection and break any kind of existing defenses against this DRA attacks. So that's it. If you have any questions, thank you for listening.
Thanks so much. It's really interesting work. I love the fact that you've also open sourced it, and actually you've got the links early on in the talk and also on the slide here to your project. We actually have a question already about this in the webinar. I would just say also, as a reminder, if you happen to be dialed into the webinar, feel free to raise your hand and you can ask your question with audio. I'm going to check out this question in a moment. Or if you happen to be in the Flower Slack, and I also will check the YouTube and other channels momentarily. But let's get things underway with this question. It says, did you experiment with structured data leakage? And so that's the tabular data. As far as I know, there is a tab leak attack for tabular data.
Yes, so we have not tested it against the tab leak data attack, but this kind of defense will work for any kind of data leakage from any kind of federated clients, because we are not assuming what kind of model is coming from the server. All kinds of assumptions from the server is taken care of. And regarding structured data leakage, we have tested with image datasets and text-based datasets, and we were able to defend against them. But yes, I am open to test it against the tab leak attack as well. Thank you for the suggestion. Okay,
that's a good answer. There's actually another question here. It is the question is the malicious layer added to all clients' local models or a subset of the client's local models? If it's added to a subset, then won't it make the aggregation difficult due to hetero local models among clients?
Okay, so this we have to shift towards the server side, because the malicious layers are added to the client's local, to the global models actually. Now, whether the model is added to all the client models or not is something which the server, which is the malicious entity, would be able to decide. However, if it's added to one of the subsets, we have to remember that the server is the aggregator and the server is the malicious entity. So now, even if the server gets the low updates from these malicious layers from the clients along with the non-malicious layers, the server can always has the rule upper hand here, right? Because the server will always be able to use only the ones that's needed for the global model and update it. It can basically remove the ones which are the updates from the malicious layers and use it for just the data reconstruction, and use the updates from the non-malicious layers for the global model update. So again, we have not made any such assumptions, but that is how the DRAs actually work.
Okay, that makes
I
sense.
have answered the question.
Yeah, good answer. Let me just see. I'll look in our Slack here. We've got some questions. 1 second. Oh, I see. Yes, this is a sort of a general question, and it's asking. Let's see. It's basically asking, what are the types of attacks you think you are not able to cope with at this stage? The ones that you sort of about that worry you if somebody wants to deploy this in a very uh, high importance scenario.
Sorry, I didn't get the question.
Yeah, I probably elaborated too much. The question is just saying, what are the attacks that you know you can't defend against currently?
Okay, so this is a defense against the data reconstruction attack, and the current state-of-the-art attacks are the low-key, derobbing the Fed, or any kind of gradient inversion attacks. So this defense will work for any kind of data reconstruction attacks right now. We have the project GitHub, and you can use any data reconstruction attack and deploy this defense. I hope it will work. But for any other kind of defenses like the membership inference attack or any other kind of attacks that's happening on federated learning systems, maybe this defense won't work. But yes, using explainable AI for model architectures can be a scope for further research.
Okay, I see. Great. Well, I don't see anything else here. So that's great. Thank you so much for the presentation.
Thank you so
Great
much.
work, and thank you for building on Flow. It's great stuff. Amazing. Thank you.
Oh yes, thank you.
Okay, so that brings me to our next speaker. As mentioned earlier, we have Mahdi Haji. He's actually got quite a few affiliations, but I believe that he can correct us if I'm mistaken here, but I think this work has been done while he's at the University of Michigan. And this work here is quite a really interesting, prominent application scenario where the types of advantages that federated systems have can often shine. In this case here, trying to detect traffic signs in highly realistic real-world scenarios, the diversity and the kind of complexity in the image makes doing that well difficult consistently. And so if you build a federated system that can have a sort of an open world approach to how it trains on the data and can adapt to different situations, you're likely to be able to build much better models. And so I'm really interested to see how he's built this and what the kind of new insights are. And yeah, so welcome. Thank you much for joining us. And I'm really interested to see the work that you've done.
Thank you. Thank you for having me here. It's an honor to be here. So let me share my screen to be able to show you my presentation. Do you have my screen? Is it okay?
Yep, looks perfect.
Thank you. Thank you. As you told, our project is about a decentralized federated learning for traffic sign detection in CAVs, which is a stand for connected and automated vehicles. And we experimented this problem in a real world implementation. So for short intro, I'm Mahdi Haji, and I'm a final year student, undergraduate student at UT, majoring CS, and I'm a research assistant at University of Michigan under supervision of Professor Wang, which I'm working on the reliability of distributed systems. And that's all that I have. So I want to present my presentation in 4 steps. First of all, I want to explain the situation that we are nowadays. So nowadays cabs, which are automated vehicle in our daily lives, produce enormous amount of data, which generates, for example, sensor data on the order of terabytes per vehicle per day. For example, to support navigation or other safety function, for example. And also, these are the real application of machine learning in our daily lives. For example, you can apply road damage detection or pothole detection, or even, for example, general object detection, human detection, obstacle detection, and so on. And also, the traditional approach was that we trained this model on a centralized server. For example, first of all, we aggregate all the data from all our vehicles, all of our clients, and then we train our model on a server, um, and then share the trained model with the other clients. But using federated learning, we have applied a new approach. For example, you can see what if we share these images to our, for example, vehicle manufacturer. It's obvious that where we are, or even if they have for example, timestamp, they can know whenever the place that we are. So it's a really issue. It's a really big issue to us, and we need to solve it. This is when the federated learning approach helps us, which you can train your model locally, and then you can only pass the um, model parameters to the server, not the data, not the pure data. And by using this, you have um, save your privacy and didn't share any personal information or personal images. So this is the approach of federated learning, and the key benefits of this approach are, for example, as I told you, privacy preserving, and also efficient communication, since you don't share your images and only share some pure integers and as a model parameters. And also it's personalized by the shared model. So the next stage that I want to explain is our complication, which are our real world challenges in a federated learning system for calves. For example, first of all, in first experiment, I want to explain that what is the best configuration for this federated system to address all of our issues. For example, we have to illustrate and examine what's the best configuration, such as number of the server rounds, or number of clients, or local epochs on each client. And then I will address the second and third issue later on my presentation. So first of all, to solve the first problem, uh, we can use a RCN, a regional based convolution neural network, which first of all it will draw a boundary box around each sign, and then detect the class of the traffic sign, which on which you can see what is the what is the traffic sign exactly, and where it is exactly, and it will help to the connected vehicle, or connected and automated vehicle. So another one thing that I want to go through is that what is the best configuration. We examine it as an experiment on Flower framework, and we implemented a fully FL system to implement this model. It was named Argos. Argos is a myth god with 100 eyes, with 100 eyes, which watching the whole world always. And we implemented this model, and we go through the best configuration, and I will explain best configuration as we experimented. For example, in our experiment, we examine task distribution, and also a local model training hyperparameter, and also federated aggregation strategy for the server. And so let's go through the results. And the first result that we got, as we expected, IID, which stands for independent and identical distribution versus non-IID. The IID was much better, as McMahon, which he is the one of the first researcher who introduced FL, as he explained, IID distribution is most of the time better than non-ID. So this is the result, which show. Let me share my laser. So this is the IID, which y-axis stand for accuracy, which on a same round servers, the IID gets a better accuracy. And also we examine server rounds, which stand for how many times the server aggregate all local models. As you can see, the more the server round B, the higher accuracy will be achieved. And also another result was we experimented in our experiment. We examined local epochs. For example, on 8 or 10 epochs provide an optimal efficiency, and with a diminishing returning beyond that. And also another finding that we had was client participation and server aggregation strategy. The client participation is a really important issue and is a really important factor to us. Full client participation achieved the highest accuracy. So we need to participate all of our clients in our training. And also another factor that is important is server aggregation strategy, which illustrate what algorithm will be used to aggregate local models on a server. So as you can see, we examine different strategy algorithms like FedAverage or FedAdam and FedProx, which FedAdam provides stable and consistent gains, but the highest accuracy was achieved by FedProx. Another question that I want to answer is that, but aren't this accuracy or even higher accuracies achievable through traditional ML training processes? If so, what is the power of the federated learning in caps? I want to answer this question by a quote from Andrew Karpathy. He was the director of autopilot vision at Tesla, which he introduced a new term, so-called data engine, which shows you will train a model and deploy it on the calves, and then you will address the rare scenarios when it's a struggle, or when you want to see rare scenarios that happen, which is an unexpected issue on the calves. So by collecting these corner cases at a scale and feeding them back to the dataset, you can address these issues on the calves. So let me go to the second problem in the real world. The second main problem is that computation resources are limited. Automated vehicles are too busy to spend a significant amount of time on training model locally. So it's in a real world, it's not possible to train a model whenever you want. I will explain it by a question. Um, how to use our resources efficiently, or the better question is how to schedule the tasks in our CAV to address to solve this problem. For example, one solution is adding more resources, which is not the best one, but it's definitely the most expensive one. But another solution is scheduling the task periodically. In a real-time embedded system, there is a programming paradigm which break task to a smaller task to be able to measure the W sets, which stands for worst case execution time. So we want to break this task to smaller task to be able to measure the worst case execution time. And for solving this issue, most of the times, real-time embedded system are scheduled periodically. So is it a good way to, for example, dedicate a task to train a model periodically? Definitely it's not, because this task scheduled offline. So for example, you will dedicate a long duration for training the model on the period on the system period. So it's not recommended to dedicate a long duration, especially for the training model, which is it not definitely a good use for our model, our resources. Another approach that we can address this question is to schedule the training process using an algorithm named a rate monotonic scheduling. So it's preemptive, which it will preempt any task with a higher priority. And for example, the shorter period and the more frequent task are, the more resources they will give. And so it's important to see their period and their and examine their period. But it's not an easy work to dedicate a period to a training a federated learning system in our calves, because we don't exact period of our training model systems. This is the explanation for rate monotonic scheduling, which more important task will interrupt other task with the less frequency. Also, rate monotonic scheduling is not always feasible. And this is the main issue. There is a theorem named Leo and Leyland. It's an old one, which shows that you need to have a summation of utilization. Your summation of utilization must be less than this term, and this is not always easy to achieve this utilization, and this is a sufficient condition to be sure that this task will be schedulable. Also, the short answer for the third question is that earliest deadline first scheduling will help us to improve our system. For example, you can imagine that you have some task, for example, human detection or robot detection and training model for a federated learning system. The first two ones are more important, and they have they have a closer deadline, so they need to be computed sooner instead of um, our training process or our training task. So the first answer is EDF scheduling, but the third challenge in our real world um, is a really hard one, and it will break the um, latest solution, which is, for example, imagine we postpone the training process while the vehicle in a garage. However, we have a long itinerary, and we won't reach our final destination before the FL server aggregation deadline. So this is not a good one, because the clients are important to us. The number of clients is important to us. So we want to participate all clients in our training process. So the last question is how can we avoid postponing the federated training process, because we don't want to lose any of our clients. I want to mention that this is different from asynchronous federated learning. In asynchronous approach, you try to update a global model independently and without waiting for each other. But this is about scheduling a training process inside a CAV resources. So this is a different problem. The first solution to solve this problem is that we can schedule a task in two types. For example, we can have a periodic task and aperiodic tasks, and with two different queues, and schedule them separately. And whenever the resources are free, we can dedicate some resource to our aperiodic task, which are our lower priority queue. For example, we can put training process in this queue, and for example, road detection, object detection, or obstacle detection in a periodic task queue. So this is higher. This is a high priority queue. A better solution for solving this problem is a RM, rate monolithic pooling server scheduling, which shows a server, which dedicate a server to a periodic, which dedicate a server in our scheduling. The server is a periodic task defined by a period and a computation time, or we can call it capacity, as you can see here. For example, we have two periodic tasks, and they have their own computation time. This computation time is examined by worst case scenarios. So we can dedicate some resources to these two periodic tasks, and whenever we have a periodic request, for example, our training process, we can behave to this process as a periodic task by dedicating the server capacity to this task, to this computation. For example, the polling server work on this way. In every period, it become active and serves pending aperiodic task, aperiodic request up to its capacity. And if there is no request exists, it suspend until the next period. For example, in here, this is the arrival time for a periodic task. Before that, we have we have dedicated a capacity to our server, but there is no aperiodic task. So it suspends until the next period, and on the next period, the aperiodic task will use the capacity of the server to, for example, train our FL system, which is a periodic task. So this was our experiment. We're currently working on our scheduling system to solve this issue. But in our study, we proved that the class-specified federated learning works, and also it's efficient for enough training grounds, and when you use methods that handle different type of data. And the next step is to focus on the scheduling for the FL training process, and we are working on that. Other collaborators of this project were Ali Reza Hosseini, Amirali Shahriari, and Sohail Haji, and our tutor was Professor Modarisi. I want to thank them. And also a special thank to Mohammed Nasri from Flower Lab, and you, Professor, and other Flower Framework team, which enable us to do this experiment.
Great. Thank you so much. You're very kind at the end there. We really appreciate the shout outs. This is great work. I want to ask before we get to any questions, I might have missed it, but you hinted that you were doing some deployments with the system. Could you describe a bit more about that? Is this going to be like used for a particular application, or is it a deployment to get access to more realistic data?
In our experiment, we use simulation approach which on the Flower frameworks. On your framework, you are able to simulate the process. For example, you can simulate a client and server that are written, for example, in Python. We are deploying on a real cab, on a real vehicles, by Dockerizing the, for example, client codes, and deploying the server codes on a real server to see more real world challenges.
I see. So this would be driving around in the Michigan area. Is that I should?
Yeah, probably. Why not?
Okay, great, perfect. Let me look at the questions that may have come up. Again, if you happen to be on the webinar, it's quite easy for me to get your question online. Otherwise, Slack and the other channels is fine. Let me take a look here. Let's see. Oh, I see. Okay. If someone's asking about applications, they were interested if this method would work for audio, and they mentioned like similar efforts to capture bird sounds. If you could do a similar thing in that context.
The real challenge on this system is to labeling them. It's not easy to label the data which you have collected. It's a real world problem.
Right. Like clicking labels from the edge, and so you're saying that would be a limitation to kind of shifting to that kind of application. Yeah, okay, makes sense. Great. I have another question here. It's quite a simple one, I guess. It's just asking, can this run on a Raspberry Pi? I think some people in the community are wondering about, doing other deployments on their hardware of choice.
We used mobile network.
Yeah.
This is not a heavy network, neural network, but it's not easy to use on the Raspberry Pis. they need resource. They need a powerful resources, but you can examine, you can simulate this on cheaper systems, but they are really too slow. For example, in our experiment, we had two. I think I'm not sure about the name of the GPUs. I think um, P200, I think. If I'm wrong, you can correct me. We used two GPUs to simulate this process, and each experiment lasts for a couple of days. It was not easy to solve. We would like to examine the real world problem. So, for example, we used a couple of gigabytes for each client to simulate their real situation.
I see. So you're saying, well, so you're saying that you're using mobile net, and so it makes it quite feasible. But there would be challenges
Yeah,
with
there would
those.
be challenges. Yeah, exactly. You need to allocate some GPUs to them, especially to train a model in a heavy data, It's not easy.
Oh, I see. So you're not a you're not doing local updates on a mobile net architecture on the Pi. You're doing
Yeah.
no. I see. Okay, that's interesting. Let me see what else I can find. I guess we'll make this the last question. The person in the webinar is asking, what was a surprising result from your experiments? Something that I guess it's a common question. I guess they want to know, when you're looking over your results, what kind of stood out to you as being unexpected?
Unexpected or expected?
Unexpected. So it was a surprise.
Huh. For example, the huge difference between IID and non-ID was an
Mm,
unexpectedly, situation.
I
Uh,
see. So you saw a big magnitude
yeah,
difference, and you really didn't expect that, I guess.
For example, in real world, you are not challenged, you are not able to dedicate a driver to label all kind of the signs. For example,
Mm.
it's better to dedicate a person, for example, to label only animal related signs, or another driver to be dedicated to, for example, warning signs. It's not easy to dedicate persons to label these signs. So the non-ID is more practical way in federated learning system, but the huge difference between non-ID and IID is unexpected.
Yeah. No, it certainly is. It presents quite a challenge. It's like yet another dimension to consider when tuning your system,
Mm.
and you can get situations that are quite realistic, but you would never encounter in a centralized case where you have full control.
Mhm.
Um, yeah, makes sense. Great. Well, we're fast running out of time, and so yeah, thank you so much for the presentation. Thank you for entertaining some of the questions from people in the community. Um, I will just start to wrap things up then. I want to close by welcoming everyone to Flower AI Day. I mentioned it earlier. Um, it is fast upon us. It'll be our first big event in San Francisco. We've done a number of events in Europe. The Flower AI Summit has grown up to be, the largest federated conference actually in the world. And we just wanted to acknowledge all the users over in the US and start to run bigger events there as well. So I'd encourage everyone to turn up and see from our wonderful speakers, people like Joe Spizak at Meta. We're really delighted to have Che Zhang from Together AI. He's the CTO. We have wonderful people speaking, as well as a lot of early releases of new Flower software. We've got some really interesting results to show everyone. So it'll be a great time. Please come out. And with that, I will also welcome everyone. Please turn up for the next community monthly. It always happens the first Wednesday of the month. And so that will be October. October's edition will be on the 1st. We try to keep it the same time as well. So it'll be 1600 UTC. If you want to join and sort of participate in some of these questions or just ask questions after the fact, we've got a special channel dedicated to this this event called Flower -monthly on our Slack workspace. And again, thank you everyone for joining us. And really, thank you also to our speakers. Thank you to Meghali. Thank you to Mahdi for wonderful work out there. They're using all these federated learning concepts and putting them into practice and really pushing the envelope as to what is possible. So thank you both for joining us today. Thank you so much.
Thank you so much.
Thank you. Thank
Great.
you.
Cool. Well, take care, everyone, and I'll see you next time.